All right, so for this next one, we're kind of doing things the other way around. So rather than being given a description of a region that we're trying to integrate over or find the area of or something like that, we're actually starting with an iterated integral, something that's already been expressed as an iterated integral. And we're being asked to evaluate it by first converting to polar coordinates. Now this, notice, is an iterated integral in rectangular coordinates, x and y. It's asking us to integrate with respect to x first, followed by y. That makes this a type 2 region, because if you notice, x is bounded by two functions of y. That's what we call a type 2 region. However, the functions that are used here for the limits of integration are difficult to work with. If you notice, once we integrate this, these functions are going to be used as the limits of integration for that inner integral. And then when I get to the outer integral, the integrand is going to become really messy and difficult to evaluate. Not necessarily impossible, but just not exactly fun. So we're going to go with the alternative and try and convert this to polar coordinates. However, in order to do that, we have to know what the region is that we're dealing with. Now remember, if this is a type 2 region, then these limits of integration are giving us a description of that region. So I want to take these limits, ignore the integrand for a second, just focus on the limits to determine what the region R should look like. If these are functions of y, I can think of this as x equals the square root of a squared minus y squared, and x equals this one down on the bottom. That's two semicircles, one on the right and one on the left of the y-axis. So we can graph those to get an idea of what it is we're looking at. Okay. In particular, these would be semicircles centered at the origin and with a radius of a. A is understood to be a constant here. Okay, so this one on the right, that's x equals root a squared minus y squared. This one on the left, x equals root a squared minus y squared, but with a negative there. Okay, and then if you look at these limits of integration, these are associated with the y-axis. So y goes from 0 to a. Remember, if this circle has a radius of a, then that's a up there. So we only want the top half of this circle if the y coordinates of the points in our region range from 0 to a. We only want this part. That's going to be what I refer to as my region R. Okay? We came up with that by looking at the limits here, but I want to reinterpret this region not in rectangular coordinates, but in polar coordinates instead. So if I were to think of R as a set of points represented by polar coordinates, R theta, then what we want to do with this is, well, we want to come up with a description of this set. So R, notice the interval that I need for R is going to be anything between 0 and a. All of the points in this region in polar coordinates have a value of R between 0 and a. 0 and a. Theta takes on values between 0 and pi. You can see that this semicircle only uses the first two quadrants, so that would put theta between 0 and pi. Okay? So that means this double integral, if I were to start by converting it to something like this, the region R, double integral over R of the function 2x plus y dA, it's the same thing as what we have here. And then up here, we want to convert this into polar coordinates by making the appropriate substitutions. The integrand looks pretty similar to the first example we did in this section, but we're working with different limits of integration, and it's not exactly the same function either. So let's see. We have our theta on the outside that goes from 0 to pi, and then R goes from 0 to a. We make some substitutions. We should have 2r cosine of theta here plus r sine of theta. And then again, my dA becomes r dr d theta. R dr d theta. All right. Now, because my limits of integration are all constants, remember a is a constant here as well, if I can represent this as a product of a function of r times a function of theta, I can separate it into two single integrals. So that's doable, and if we kind of think of what we did in the first example in this section, I'm going to get my first integral from 0 to theta. It's going to look like 2 cosine of theta plus sine of theta d theta. And then the second integral goes from 0 to a, and it's going to look like r squared dr. And then it's pretty straightforward from here. This gives me 2 sine of theta minus cosine of theta from 0 to pi. And this guy is going to be r cubed over 3 from 0 to a. Working all this out, what we end up with at the very end is 2a cubed over 3. Not too bad. Okay, so I think there's a couple of problems in the homework where you're asked to do this. And again, notice we didn't do anything with the integrand when we came up with this region. The region comes entirely from the limits of integration here and here. And you have to remember, with the dx and dy indicate that we're looking at a function of x and y, functions that are represented in rectangular coordinates, not polar. We recreate this region and then rethink the points in that region in terms of polar coordinates, then go to your double integral and convert to polar there. Okay. I have one more example that we're going to do, and I think I'm going to do it in the next video, but I want to preface it with a quick little discussion from probability theory. So not all of you have had statistics and probability, but I think pretty much everybody's heard of the bell curve before. So this is my coordinate plane here, y and x. Probability and statistics, you spend a lot of time working with this thing called the normal distribution. And in particular, one that we keep going back to is the standard normal distribution. Standard normal distribution. This is not a probability theory class. This is not a statistics class. I'm not concerned with you knowing the terminology I'm going to talk about, but it gives us one kind of interesting example where we can use double integrals and converting to polar coordinates. So in probability theory, you have these things called PDFs. They stand for probability distribution functions. And we use them when we talk about continuous probability distributions. None of those terms are important for you to know. What is important is that in probability theory, if you have a PDF, it gives you the graph of a curve. It's a function of x. And in order for it to qualify as a probability distribution, the area underneath that curve has to be equal to 1. That's necessary for a probability distribution. And this particular area, it's my kids again, that particular area under the curve, you can think of that like an integral, but in this case we're integrating a function from negative infinity to positive infinity because this curve goes forever in both directions and we want the total area under that curve. Now, the standard normal distribution has this function. It's equal to, it's y equals 1 over the square root of 2 pi e to the negative x squared over 2. Okay? And in order for this thing, like we said, to qualify as a probability distribution, we need to know that the area under this curve, or in other words, the integral of this function, I could pull the 1 over root 2 pi out e to the negative x squared over 2 dx. I need to know that that's equal to 1. And the difficulty here is that this function does not have an elementary antiderivative. This is one of those functions that you usually take a look at in Calculus 2 and say there's a few functions that just cannot be evaluated using antiderivatives. This is one of them. So the question is, how then are we expected to know that the area under this curve is 1? How are we supposed to evaluate this integral? Well, notice, first of all, this integral is the same thing as showing this. E to the negative x squared over 2 dx is equal to the square root of 2 pi. And it turns out, using kind of a clever trick, we can think of this as something that comes out of a double integral instead. And then that, with the use of polar coordinates, helps us evaluate that double integral, and we can eventually get to this. So I'm going to use the last video for this section to talk about how we can show that this integral is actually equal to the square root of 2 pi.